Now we're going to figure the primary overcurrent protection device based on 250% times the primary current. And remember, when you increase above 125% times the full load primary current of the transformer up to say 250%, then you have to put the 125% and place it in the secondary of the transformer. Now, this is due to inrush currents problems that might occur, and you trip that primary overcurrent device at 125% of this primary current. Now, if you know the resistance of the windings, then you can take primary current is equal to 1.414 times the voltage divided by the resistance of the windings, and you would get the peak current. Inrush current then would equal this peak current calculation that you made divided, or excuse me, I got that backwards. Let me restate that. You would have the inrush current equal the full load current of the transformer divided by the peak current that you calculated, and you would come up with an estimate of the inrush current. Many times, most all the time, electrician in the field won't have that, so we used to use the clearing time of the overcurrent device. We figure 10 to 12 times if the overcurrent device would clear in 0.01 second. If it, say, cleared 0.1 second, then we'd figure over 12 up to about 25. If we had an overcurrent device that would clear, at 0.0084 seconds, then it might be a little higher than 25 times. So this was an estimate, though. We're not saying that that would give you the exact inrush value. Now, so what we would do on most all of our transformers, we just figure 10 to 12 times, and that was pretty a good estimate to use. Now, notice this transformer is 50 kVA, as the illustration points out, 480 volt three-phase primary, 208 volt three-phase secondary. The primary is a 3-wire, and the secondary is a 4-wire. And then notice the overcurrent protection in that primary, as you see in the illustration, is 250%. Our equipment grounding means we're using EMT in accordance to 250.118 is our equipment grounding means, which is legal. The system bonding jumper that you see there is sized according to table 250.102 C1 of the code, and that's identified as a system bonding jumper in 250.30 A as in apple 1. The grounding electrode conductor is sized from table 250.66, and notice we would reference 250.30A5 and 250.30A4. And then again, caution is illustrated here, is that the secondary full load amps is at 125%. So reviewing the illustration, next we will calculate the size of the primary overcurrent protection device as well as the secondary overcurrent protection device using the 250% rule and the 125% rule is outlined in table 450.3b. Now notice you can reference our chapter 9 and look at figure 9-13 and go through that series of figures, and we will size the secondary transformer conductors using the tap rules of 240.21c as in car. And that's in Stallcup's Electrical Design Book, Volume 1, or go online in YouTube and look at those videos, starting with figure 9-13, and then they're just in systematic order there. So Remember this, 450.3 of the NEC and the informational note protects the conductors either using 240.4 or 240.21c for 1,000 volts or less. So we know that 450 protects the transformer. 240 is the overcurrent protection means to protect the conductors, and we size the conductors using table 310.16. Now this illustration 20-12 is illustrating the 250% or 125% rule in accordance with table 450.3b for primary and secondary protection.